But isn't this also an answer to that? Maybe we should take that offline since Mike's is short of time. But you could analyze a small part, and if you find out later you executed another part and it was wrong, you treat it as if it was just loaded. I don't know.
Yeah, we do this all the time in Hotspot. There are regions of code, people have write exception handlers that are never taken. We just write the bailout to the interpreter on that path, and we cut off optimization there. And then we go to places that are hot, and you inline like the devil, and then you don't bother doing real interprocedural analysis. You all do it within a giant inline method. But it's all the uncommon paths have been trimmed off the edges. So you have a big single compilation unit. You did a good job there, and that turns out to be good enough. If you fall off one of these funny odd edges, you recompile that method, knowing now that you can take this funny odd path, and maybe your inlining is different. All works out well.
Myth number 3 is online profiling is too expensive. This is too much overhead. And there's different ways of categorizing profiling. I'm going to talk more about sort of program instrumentation, so the VM or the compiler inserting profiling. Certainly, if your hardware is giving you for you, then it's not going to be expensive. And there was a paper by Intel this year in PLBI that uses that. So there's 2 techniques I'm going to just point out. One is basically a patching kind of technique. I don't think it's terribly new. It's probably somewhat obvious. Where you basically take some, you want to insert profiling, here's your code, and so what you do is you insert a jump to your instrumented code to gather wherever you want, and then jump back, and then when you have enough profiling information, you get rid of the patch and restore. Another technique is different, called full duplication. Here it is definitely a code space hit. Basically says you take the code you're interested in, think of this as a method, you duplicate the method, so you've got you duplicate the code, you got the same code over here. This piece of code you put all your instrumentation in, and then when you go to these diamonds, periodically, like once every 1,000 times or 10,000 times, whatever it may be, you jump over to the instrumentation code and gather whatever you're looking for, and then jump back and stay here most of the time. So you have the overhead of these red diamonds, which I think are about 4 or 5%, and then you only get this high overhead, statistically, not too often. Okay, so that was a quick and dirty hand waving that you can do online profiling. Static is greater than dynamic. That was my summary for that. So this basically says if you're going to do a static compilation of the whole, the system, you'll be able to get better performance than dynamic. And we've touched on this a bit before. I think Bob mentioned this a little bit. And the answer to this is basically feedback-directed optimization, in particular online feedback-directed optimization. There are lots of places inside the compiler where you have heuristics trying to guess what's going to happen. And if you actually have cheap information, profile information, those heuristics can be a lot smarter. Okay, so this is, just think of this as what used to be the profile-guided optimization, or training run, then you do optimization. Well, now you get rid of the training run. It's just V-run, and you gather profile information, and you compile. Using that information for heuristics. So just some numbers. Here was Jenks RVM, those same benchmarks. This is about 10%. This is, I would say, a lower bound, because there was only 2, well, I guess not, there was a few optimizations that were implemented that actually used profiling information. I'm sure commercial JVMs will have a better bar there, better improvement. Here was numbers from 2001. I think this was about 6%. Again, this is just to show you it actually exists already, people are using it, and it gives you a performance win. Yeah, Mika.
I'm surprised you gave this answer to this question. I would expect something different. It seems to me that this answer should actually be used as to help static optimization, because you could do feedback-directed optimization offline.
Right.
Green runs, which is offline static and not dynamic.
Yes, so you can do that, but do people want to do that?
Yeah, the management of that is such a pain.
Yes.
So the advantage of online is not that you get better performance numerically, it's that it can all be managed by the VM, and
it'll actually get used.
Yeah, it'll actually get used. Right.
It won't be just a spec publication.
Yes. So
So there's a cost. You know, you show a lot of benefits here, but I don't see the overhead. I have yet to see overheads measured in terms of the memory footprint of all these mechanisms.
Yes, I have.
Is it on
I
server
have a
VMs?
slide like slide number 120.
Okay, well, yeah, I can.
But not-
Servers are great. I love servers, but I also think that there are other machines out there,
Yes.
and certainly a handheld, for example, is going to have a hard time. Collecting all this information. Having a big, heavy-duty compiler in there, etc. So,
Right.
So what's the story in that space?
It's coming up.
Okay.
Well, it's not really a story. It's going to be, this works well, except for if you're on a memory-constrained device, you still want to do something like ahead of time, but you can't do it.
Or you can do offloading.
On a server.
On a handheld device, you can basically do the important stuff on a server somewhere.
Right.
Communication's free.
My handheld device doesn't have.
Well, if you have a powerful enough server, you can actually just run, just predict or do speculative execution of what the handheld is doing.
That depends a lot
In
on
parallel.
all of the applications and the network and
Right.
a lot of things.
All right, so this is just a laundry list of some of the things you can do with feedback directed optimization. I'm not going to spend a lot of time. There's inlining. Cliff can tell you more about this than I can. Basically, the idea is if you're in method D and it trips some kind of counter that says, hey, this is hot, you don't just go and recompile D, you crawl up the stack and say, I'm going to have knowledge of my inlining heuristics and keep going up until I get to a point where I know I won't be able to inline the whole thing. So this is a one way of getting more of the program like Cliff was talking about earlier. More of the program to analyze.
But I think it's a good question to put to the one that Ben pointed out on the
Yes.
board, which is sort of client versus.
Yep. And you'll probably touch on it
I'll talk on it a little bit.
a little bit.
So how do you want to phrase it?
Footprint for clients?
Yeah,
Or these
Compilation
techniques?
strategy.
Yeah. Compilation strategies
For handheld.
Yeah.
for disconnected handhelds. All right. Code positioning, it's kind of obvious. This just basically says if you know something is hot, you might as well put the hot blocks next to each other and cold elsewhere. Famous Pedersen-Hansen mark. Multi-versioning. This is a picture here. So here's an example where you're basically testing to see, you've got a call to foo, and you're trying to see where it's going to go. So you can do a test to see if it's going to be a particular instance of foo, inline that guy, and if not, do the general mechanism. I think almost everyone does this. One thing that's kind of interesting is and I think Cliff was mentioning this, is that if you have on-stack replacement, you basically say inline that, and if I happen to go this way, then I will bail out into my interpreter and fix up later. So it's another form of speculation. And then so on. All these heuristics can use profile information just like they could before with offline profile guided optimization or feedback directed optimization. Okay, so here's the summary. And the fourth bullet there, however, ahead of time compilation still need, this is my escape. All right.
So Mike, just a
Yes.
comment. I think there's clearly a lot of the potential still hasn't been tapped here. In
Yes.
terms of, we've just talked earlier about optimizing frameworks, optimizing middleware. So for example, we have a project in research where we're looking at XML applications. And at runtime, if you can customize the code to a specific XML schema and a specific set of XPath queries, you can end up specializing the code and getting factors of improvement that go even beyond this level of optimization. So when those technologies kick in, then I think the crossover should be more convincing.
Yes, and that
Point
leads to
is
the next
remained.
myth, actually. That's good.
Yeah.
Mike,
Yes.
just very quickly, I think the other side of that is we should be clear on the fact that even static compilers don't have an unlimited amount of time to do analysis, right? So that's a myth in and of itself, and also the fact that programming languages which have very dynamic semantics, if you try to compile them statically, you may end up with far poorer results than even a simple dynamic compiler.
Yes, yeah. Okay, optimization is dead. We should all be doing something else. Software engineering seems to be popular.
Roasting's law?
Yeah, Probstein's law.